Hi, everyone. Welcome to another episode of Q&A about the future of science and technology. I was away for a little while, actually most recently at an event that really had quite a lot about the future of science and technology. It was an event called MARS. It stands for Machine Intelligence, Automation, Robotics, and Space. A event put on by Jeff Bezos and the Amazon crowd. From its name, it has to be in March, so it was in March. Got to see all kinds of exhibits, talk to all kinds of people, so maybe I'll be able to talk a little bit about that here. But let me see the questions that have come in. So I see one from Taki. What roles do category theory and type theory play in our understanding and future of mathematics? Oh, wait a minute. It looks like I already talked about that at some point. Oh, I talked only about the history of category theory. Well, let's see. Let's talk about that. Very different from robots and spacecraft and things of that kind. There's kind of a question about how one should think about mathematics. What is mathematics? What kinds of things is mathematics talking about? And back, in the distant past, people thought of mathematics like in the time of Euclid and so on, as we're talking about lines and points and angles and triangles and so on. Things that we kind of think of as being things that we can explicitly imagine in our minds, or that are kind of like the things that show up in the real world. Then towards the end of the 1800s, there was this real push towards sort of the abstraction of mathematics, thinking of mathematics as a purely formal system. I mean, famously, David Hilbert kind of had this way of thinking about mathematics as just this sort of symbolic formalism, where he said, well, you could as well be talking about tables and chairs as talking about numbers and lines and points and so on. That it really is just a formal structure where you start from certain formal axioms that say things like, x dot y equals y dot x. And we don't really say what dot is, but we just say it has that property. And then you build things up from those formal axioms. And that's kind of the tradition of mathematics that people often sort of go back to when they say, what really is mathematics? What is it really grounded on? They say, well, it's all these axioms. And maybe there are particular axioms like the axioms of set theory, for example, which are the things that are the grounding for mathematics as mathematics is thought about. Now, the truth is that actual working pure mathematicians, unless they're into these foundational areas like set theory and so on, that's not at all how they think about mathematics. They think about mathematics more in terms of the kind of conceptual development and the sort of the concepts of how different kinds of things, different abstract kinds of things fit together. The structure of a space, the mapping from one space to another, things like this. Not thinking about that in terms of sort of formal kinds of structures. Now, for example, in our efforts to build Wolfram language and Mathematica, in a sense, we have to take the things that one wants to do in mathematics and turn them into something that is fully formalizable, fully turned into kind of this symbolic computational sort of direction. And that works really well for many purposes. But when you're looking at kind of what's sort of the foundational stuff that's going on in mathematics, there's kind of this idea that in principle, it could be done in terms of axioms. In practice, mathematicians do it in terms of the concepts that they think about and how those fit together at a conceptual level, rather than sort of thinking about them in terms of sort of the microstructure of axioms and so on. But then to sort of make these things really solid and computational, you do have to think about them, not so much in terms of axioms, but at least in terms of symbolic expressions and transformations for those, which is sort of the basis for Mathematica and Wolfram language. And in a sense, the success of Mathematica over the last 38 years or whatever is a great demonstration of the fact that math and many, many things around it, but math in particular, can be usefully represented by sort of symbolic expressions and transformations for symbolic expressions. Okay, so how do type theory and category theory fit into this picture? Both of them are sort of alternative attempts to formalize mathematics. They're ways of kind of saying what is the structure, what is the sort of formal structure of mathematics that goes, that is not kind of built up from axioms quite, although they both do have axioms, but it's not so much sort of we're going to define things. I would say that the traditional kinds of axioms that people look at are in a sense very algebraic axioms. They're things that say things like, imagine the plus operation. Then with respect to the plus operation, x plus y is the same as y plus x. It's kind of like there's an algebraic expression that is equal to another algebraic expression. Well, type theory and category theory are a bit different. So let's talk about them separately. Let's see, we can start with category theory. So category theory is an attempt to kind of get beyond kind of the level of talking specifically about x plus y is the same as y plus x, kind of talking about things in terms of their kind of explicit symbolic structure, but more it talks about kind of the overall kind of connection of different kinds of objects. So for example, there's a notion of a category, there are objects in a category, but those objects aren't kind of explicit things like the number 2 or something like that. Those objects might be the set of all numbers, or some sort of functions on the set of all numbers, these kinds of things. And then there's the idea of morphisms, which are you're going to get some way of transforming from one object to another object, but you're not really being very explicit about what that you're saying there is this mapping from here to there. And it turns out that quite a lot of the structure of mathematics can be described at this category theory level. You're kind of giving an outline of how the math works. In the end, if you want to sort of implement the math, you'd have to go in and say, well, what actually is this morphism? What transformation are you making? But you still can get quite a long way by just saying, what's the overall structure of what's happening in the math? And I would say that in category theory is sort of useful for getting an overall sketch of a mathematical area and for sort of organizing the math you're going to do. When it comes to actually saying, well, what really happens in the math, then you have to drop down below that level most of the time. There are sometimes you may be able to prove results, establish things just by looking at the level of category theory, just by looking at the kind of sketch of the structure, so to speak, without having to go into more details. Now, I will say that category theory, I think, it has many assumptions about sort of how math works. One of the more important ones is that it says whenever there's a morphism that goes from one object to another, morphism from one object to the next, a morphism from that object to the next one, morphism from that object to the next one, then it is sort of an axiom of category theory. Then there is also a morphism that goes from the first of that sequence of objects to the last of that sequence of objects. In other words, you can always jump. There's always a morphism which is kind of a jump ahead morphism that doesn't have to go through each step. Now, the fact is, when you think about things in an explicit computational way, you can't always do that. You often have computational irreducibility, where to know what happens, you kind of have to explicitly follow each step. And category theory is kind of denying that possibility. It's saying there always is that morphism that just jumps from the beginning to the end. It doesn't say that morphism is a much more complicated morphism that has to do much more computation. So in that sense, it's kind of summarizing certain kinds of things that are computationally reducible. But in general, it's kind of a sketch of sort of how mathematics is put together. We've experimented with category theory. There's a bunch of packages for category theory in Wolfram language. I haven't really found it all that useful as a way to kind of sort of give a sketch. You might say, well, it could give an outline of a program, let's say, an outline of mathematical operations. I haven't found it terribly useful in practice for that. Part of the problem is that one of the key ideas in category theory is the idea of functors. When you have a category and a string of morphisms, another category, a string of morphisms, there's a functor that can translate from one to the other. In the case of in an explicit kind of computational representation, that functor has to essentially transform a function to another function. But when that function is represented explicitly in symbolic terms as an actual transform this to that, add these numbers together, whatever else it is, it's very unclear how to take a function and kind of do what one might call metaprogramming to change that function into another function. Just that is not a very natural operation to do when one is doing explicit computation. I don't really know how to do it. If one could figure out a nice way to do that, that isn't just saying there exists a way to transform from this function to that function. I mean, in mathematics, it's very common to just say, this thing exists. We're not going to say what it looks like, but it's important to know just that it exists. Well, that's sort of the story often with these kinds of things. And I think the way that, without some level of explicitness to how that functor acts to change one function to another, it's kind of hard to bring that down to the level of explicit computation. So let's talk about type theory. Also asked about type theory. So type theory, I mean, it has very sort of its origins in set theory and so on in the beginning of the 20th century are a bit messy. But when it comes to sort of computer kinds of things, the sort of why we talk about types is because the intrinsic hardware of computers will distinguish, operations on integers from operations on floating point numbers and so on. And it's useful to say the type of this thing is, it's an array it's a tuple of 3 integers, for example, list of 3 integers, let's say, because that tells you at a low level how to lay that out in the memory of the computer and what operations you can do on it with directly in sort of the machine code of the computer. So type theory is, again, a way of kind of, it gives you a way of giving a sketch of what's going on. So you say, I have a function that takes lists of 3 integers and returns functions that take real numbers and return real numbers, let's say. That is a type. The specification of I have a function that has this property, that property, that property, that has this kind of eats this input, produces this output, and so on. That's a way, that's the notion of a type. And that is, again, kind of a way of getting a sketch of what happens in mathematics, is to use this idea of types. Now, it's not saying necessarily, I have this actual explicit object mathematically. It's rather saying I have this thing that roughly has this form. And when you can prove things just in terms of types, that's like in category theory, where you can prove things just in terms of structure without having to drop down to the specifics. Now, in type theory, there are some slightly technical things. The question is, it's usually said, is a type inhabited? So you say, I have a thing that maps this to that and has this form with integers and this and that and the other. And the question is there an example? Is there anything that has that structure? Because if you say something is both, I don't know, a list that is both has length 0 and has length 1, that's not going to be inhabited. There is no list that has both length 0 and length 1. But it turns out that the finding a something which is an example of an inhabited type, takes a type and says, this is an example of something that has that type, that turns out to be equivalent to finding a proof. And kind of the notion of, is there a way to transform from here to there, is equivalent, something called the Curry-Howard correspondence, to the question of whether there is a way to find an example that has this type. So that's kind of a sort of a formal way of sort of meshing together sort of some traditional mathematical development with just this sort of sketch based on types. Now, there's a sort of more fancy version, so-called homotopy type theory, that sort of kind of ascends into the level of talking about kind of types as structures in their own right. Same kind of thing in category theory. There's the notion of higher category theory, where you're having all kinds of transformations between categories and higher categories and monoidal categories and all kinds of elaborate stuff, just sort of operating at this sort of sketch level. But both category theory and type theory have kind of a rich formal structure that can be investigated. And in fact, in both cases, there are sort of interesting and important things that happen. So, for example, in our physics project, you can kind of think of things which correspond to features of the natural world, features of physics, as being things related to categories and higher categories and so on. So, for example, the notion of the structure of space turns out to be related to well, let's see, actually, no, the sort of branching that happens in quantum mechanics is related to symmetric monoidal categories and things about kind of the correspondence between different parts of that and causal graphs are related to higher categories and so on. There's a whole kind of formal structure that leads you to some interesting things. And there's kind of a limit of all those things, which is the higher categories. So there's kind of mappings between, this is getting complicated. This gets quite complicated. Okay. In mathematics, for example, a proof is often a thing that says, this is equal to that. And you say, this is equal to some intermediate thing, which is equal to another intermediate thing, which is equal to another intermediate thing. Eventually, it's equal to the thing you wanted to prove that the first thing was equal to. And so a proof is kind of this many-step thing where at each step, you might be just using the original axiom you defined to say, I can go to this next intermediate, next intermediate, next intermediate, and so on, until eventually I get to the result. So a proof is sort of this mapping from the left-hand side to the right-hand side or something. And then you could ask sort of at the higher category level, you can ask, well, let's look at a mapping between proofs. We say we have one proof, there may be two different proofs of the fact that sort of A equals B. There may be one path and another path that both lead from A to B. And so you can look at a correspondence between those proofs. That's where the term homotopy, well, this is, again, we're sort of, there's this kind of complicated merger of things with categories, things with types. The homotopy type theory idea is sort of talking about things like homotopy is this kind of, can you take a curve and deform it into another curve with the same endpoints, for example? And that's relevant if you're saying, oh, I have like a torus and I have a curve that's going kind of the long way around a torus, a donut with a hole in it, and a curve that's going around the short way around the torus, and those can't be continuously deformed into each other. So similarly, if you have something that is sort of the curve, the piece of string wrapped around a pencil, if it wraps around once and it wraps around twice, you can't continuously deform those things into each other. So that's the notion of homotopy, and homotopy type theory talks about sort of in the space of possible proofs, can you continuously deform one proof of something into another, or is there sort of a hole in the proof space in essentially a mathematical space that prevents that deformation? I've looked at this quite a bit. I think in traditional homotopy type theory, there's actually rather little that you can say at a really formal level about those kinds of questions. But empirically, you can just look at possible proofs of things and you can see quite a bit. In any case, there's this notion of sort of higher category theory, sort of these higher proofs, mappings between proofs, mappings of the equivalence between a proof being equivalent to another proof. And then there's a mapping between the equivalence between proofs to other equivalences between proofs. If you take that whole giant stack, you get to this thing called the infinity groupoid, which is kind of this limit of higher category theory. And it turns out the infinity groupoid is deeply related to the Roolead, the thing that I've introduced and studied quite a bit, which is the kind of infinite entangled limit of all possible computations. This is kind of going off, this is kind of the most extreme abstraction you can kind of imagine. The Roolead is kind of the ultimate form of abstraction. And it turns out that it's actually very much the same kind of thing as the infinity groupoid, which is sort of also the limit of this abstraction of things like mappings between equivalences, of proofs going up to infinity. Okay, what will this actually do for mathematics and the future of mathematics? It's a good question. How much of mathematics is captured by these kind of idealized sketching techniques? In a sense, what we've done in building mathematical and Wolfram language is also an idealization of mathematics. And that's turned out to be a really useful idealization of mathematics. How useful is the category theory idealization? How useful is the type theory idealization? They both have some use, and they both have a use in kind of organizing the way that you present proofs and you do mathematics and so on. They haven't sort of slam dunk solved mathematics, not that anything can. That we could easily see that that's not possible. It's sort of a consequence of computational irreducibility and Gödel's theorem and so on, that you can't just have a thing that just takes any piece of math and just says, okay, I can solve it all and jump to the end. But are these the right models for sort of the way that the structure of mathematics works? That's not clear. I kind of tend to think that they're actually not quite the right model. I made a big effort to sort of study the sort of physicalization of metamathematics, the kind of thinking using ideas from our physics project to study things like the space of all possible theorems and so on. I kind of think there are different directions that one can go that are more faithful to the sort of empirical metamathematics of what people have actually done in mathematics. So I think there's a lot that can be done in those directions, and whether one can sort of glue that onto category theory and type theory is not so clear to me. I think, as I say, I think there are some that they're useful up to a point. Whether they will be the future of mathematics, I really don't think so. They're sort of it's a little bit like saying the following. Let's say you're speaking in English and you say, well, I can reduce everything I'm saying to logic. Well, that's not really right. There are certain things that are well organized by talking about them in terms of logic. If this, then that, this implies that, and so on. That's, but it would be wrong to think that everything that I can express in language, I can express with sort of in the formal structure of logic. And I think that's kind of the same type of thing that's happening with category theory and type theory. They're both useful in the same way that logic can be useful, but they're not the whole story. And that's and there are other stories like the sort of whole world of the sort of physicalization of mathematics and empirical mathematics and so on. That's a bit of a different branch. Let's see. Okay, let's see. Well, a lot of questions here. Let me just, Meta is asking, what would be an example of a hierarchy of types in theoretical physics? Okay, it's okay. Let me try and see if I can say this in a reasonable way. So in our physics project, there's the notion that sort of everything in the universe is described by this hypergraph that whose nodes are the atoms of space and whose hyperedges are relations between the atoms of space. And time and things happening in the universe is all associated with update events. This piece of hypergraph is rewritten to that piece of hypergraph. And then what's really important is the causal graph that represents kind of this update event affects this other update event. You have to have done this first update event before you have the stuff that's going to go into the second update event, so you can do that second update event. It's kind of like functions in a program. You can say, well, I've got to run the function G before I run the function F, because I'm going to use the output from the function G to feed into the function F, and so on. Well, so one thing is kind of the notion of the sort of sequence of things from event to event to event, a so-called time-like curve. That's sort of one type of thing. Then we have the correspondence between different time-like curves. That's giving us so-called space-like hypersurfaces. That's telling us we've got these different events that are happening, sequencing through time. But then we want to say, if we go sort of in the transverse direction, we say, well, what events can we think of as simultaneous? That's defining the space-like hypersurface. That's a thing where we are looking at essentially a higher type, because that is something which is not looking at this kind of just a function applied to this makes that in this sort of single curve, but we're instead looking at these slices that go across many curves. And then we can go beyond that. We can look at multi-way causal graphs and things like this, which are yet more correspondences between these kinds of things. And that's sort of a little bit the hierarchy of types, an example of a hierarchy of types thought about in physics. So, one of the things that happens there is some of those types are things that we care about, like, oh, it's things happening through time. It's things happening at different places in space. It's things happening on different branches of history and quantum mechanics. And then there are things when we go to higher and higher types, which are a little bit beyond what we currently are thinking about. We have this notion of space, we have a notion of time. there are sort of higher correspondences, which I, I don't know. I think they're a little bit beyond what our minds kind of at least are able to capture right now. So I think those things are sort of the limit of those things is the Rulliad, which is this sort of this very, very big thing that sort of encompasses everything that could be, but is something that is very hard for us to imagine except in tiny slices. Let's see. Question from EI. Would you ever take a trip on Blue Origin or SpaceX? Do you see more for the future of space travel happening sooner or later? You know, one of the things on this event I went to last few days, I did get to see a rocket launch. I've actually never seen a rocket launch before in my life. Quite a number of times, particularly in the 1990s, I knew people, astronauts who were flying on particularly the shuttle and so on. And I was like, they were like, oh, you should come and see the launch. But I was very busy working on a big science project and so on, and I never got around to doing it. So I finally got to see a launch and learn that, you know, you can tell what kind of fuel the rocket has by whether it has a yellow flame at the back or a white-blue flame at the back. Yellow is for things like methane, white-blue is for liquid hydrogen-oxygen mixture and so on. But in any case, you know, when you watch a rocket launch, it's from quite a big distance. So it's really just a little thing that goes up. And then you know, 8 minutes later or something, in modern times, something comes down as well. And the booster rockets land again. Very impressive. I think it's a good example of use of algorithms, actually, to be able to make that happen. Apparently what's going on is that there are sort of optimizations that are done of, you know, exactly how much should you fire the rockets in this direction or that direction, and many times a second. I think it's kind of looking at all these different parameters of what's happening with the rocket, and it's running an optimization procedure, so-called convex optimization method, I think, to figure out, you know, what should you do next. It's quite an interesting kind of, it's sort of a more advanced form of autopilot than one's seen before. It's kind of a next level of control theory applied to that lets the rocket actually actually land again. Am I up for space travel? I don't think so. I'm pretty conservative about those kinds of things, and I'm more kind of into, well, it'd be interesting to see that different perspective of the world, but I'd be kind of happy to see that in a virtual reality setting rather than in a sort of personal kind of a personal experience like that. I mean, it might be kind of interesting to be in a weightless state. I suppose I could take one of those parabolic flights and where you're in a plane and the plane is imitating the motion of a thing that's just falling so that you are weightless. It only lasts I think maybe a minute or two, maybe a little bit more than that, before the plane has descended from whatever 40,000 feet or something down to, if you descended any further, you would crash type thing. But it certainly would be interesting to be in this kind of to experience weightlessness. I think, you know, sort of one's intuition about physics probably changes a bit. I've certainly talked to lots of astronauts and asked them all kinds of questions about how different kinds of things work in weightlessness. I mean, you know, when you have water, for example, it's just a big spherical blob, and you can kind of blow on it and it wiggles around and things like this. You know, it's a big problem if the blob shatters because you get little pieces of water all over your space station or whatever, and then you have to worry about sort of vacuuming them up again. I mean, there are all kinds of effects. Actually, one that I learnt from an astronaut at this event I was just at, which I didn't know, is if you're asleep and you're breathing out carbon dioxide, unless you have a fan taking that carbon dioxide away, the carbon dioxide will just sit in front of your nose and asphyxiate you. So that's a thing I didn't know. I mean, if you think about the physics of it, it's not terribly surprising that that would happen, but I hadn't thought of that. And I think it's sort of an interesting thing. You get to, in weightlessness, you get to sort of refactor a lot of things that you might have imagined in that refactor how you think about things relative to our typical experience of in gravity behavior of everything. And I think the a lot of physiological effects, the fluid, where fluid is in your body changes when there isn't gravity pulling it down to your lower extremities, so to speak. And lots of things, no doubt. I was asking somebody actually whether you get taller when you're weightless for a while. They actually didn't know. So although they said that they'd had a back problem that had gone away when they were on the space station for a while. So that's I'm not sure that that's necessarily the most efficient way to cure a back problem, that is to go to space. I think it could work the other way. Apparently, it's kind of a difficult thing when you get back into gravity again. And I think for future long-time space missions, the idea that's long been floated, so to speak, of rotating your spacecraft or space station so that you have artificial gravity from centrifugal force is probably a thing that people want to do. But in any case, I guess the question here was kind of future of space travel and when it will happen and how it will happen and so on. And there's sort of space tourism versus all the various uses of space. I mean, I think what's become clear is that the whole telecom infrastructure and the Starlink story and the Project Kuiper story and all these kinds of things of putting low Earth orbit satellites to do cell phone-like communication, that really does seem to be a thing that's going to work. And I think there are kind of so that's a thing that's working. The thing about remote sensing, looking at the Earth from space and looking at it and taking a picture every day and things like that, I would say it's still unclear. There are a number of companies that have satellites that are taking a picture of everywhere on the Earth, a reasonably good resolution every day. And what exactly you should do with those pictures is not really completely clear. I mean, there are two known clear applications: military applications and finance applications. Hedge funds that want to figure out, ahead of everybody else, what's the crop yield going to be, or what or how many cars are in this retail establishment's parking lots, and what would their sales be like this Christmas type thing. But whether there is a consumer application for frequent imagery of the Earth is still not clear. I mean, somebody may figure that out one day, and that will be a big sort of boon to remote sensing. But I think that's really unclear. And a number of the companies that are doing that kind of thing have struggled a bit because it's just not clear who the customers are, other than military and some finance type customers. I think, and maybe some agriculture customers as well. But I think more on the finance side of agriculture, of what should the futures contracts for corn be like right now, than the what plants should what should I plant in my field kind of thing. Now, I think when it comes to sort of other applications of space, I mean, clearly the things like GPS, and now there are a bunch of different GPS constellations that have been flown by Europe, Russia, China, etc., in addition to the sort of core US one. That's clearly a useful thing, and that's sort of an interesting direction. One thing I learned, I didn't know this, is the question of how do you navigate on the moon? Because there isn't a GPS constellation on the moon. There aren't GPS satellites orbiting the moon. On Earth, what happens, how does a GPS receiver work? What's happening is there are all these satellites, it's quite a large number now, that are orbiting the Earth, and you're kind of triangulating. You're saying, I know where these satellites are going to be. How long does it take a radio signal to get from that satellite to my receiver? If I know that for 3 different satellites, then I can triangulate to find the position of my receiver. And the way it works is the signals that are sent from those satellites have these sequences where you can precisely kind of line up what was the delay from the satellite. And there's been some sort of fuzzing of that signal because particularly the US military has kind of for a long time was reserving kind of the most precise data for themselves, although that's mostly opened up at this point. And there's sort of ways to get more and more accurate in knowing where you are to within, a meter, 5 centimeters, things like this. Sometimes that requires very detailed information about kind of the propagation of radio signals through the ionosphere, and exactly how that timing works. I think these days there's like tens of trillions of signals that are being sent and received, for example, from Starlink and things like that every day. And there's very detailed information at this point that one has the potential to use to figure out kind of these delays and to make GPS more accurate. But something I didn't know was when it comes to navigating on the moon, you're kind of out of luck for GPS because the GPS satellites are orbiting the Earth, not the moon. And you might say, well, why don't you put up a constellation of GPS satellites on the moon if you want to navigate on the moon? The moon is an awkward place to orbit. The Earth is pretty close to a sphere, and its gravity field is pretty close to a spherical gravity field. The moon isn't that way. The moon has, for example, a great big lump on one side. I mean, the outer surface of the moon is a sphere, but the density of the rock inside the moon is not uniform. And presumably that's because when the moon was formed, there were sort of two big blobs that got smooshed together, and the gravity made the outer boundary of the moon be roughly spherical, but the innards are not of uniform density. And so when you try to orbit the moon, you don't get the same kinds of nice circular orbits and so on that you get on the Earth. The orbits have more complicated form, and you have to put lots of effort into getting a stable orbit around the moon. Actually, I don't think there have been orbits that have been stable for that long around the moon yet. You can obviously keep orbiting the moon by firing your rocket thrusters every so often to sort of keep you on track. But in terms of just passively orbiting, that's a somewhat difficult thing to do. But the thing I learned is that actually the Earth, there was an experiment done on the most recent lunar lander, I think, the Firefly lunar lander that just landed a few weeks ago. I think it was on that one, that where you can actually see the terrestrial, the Earth GPS satellites from the moon. And so a GPS satellite orbiting the Earth is sending most of its radio energy down towards the Earth, because why would you send it out into space? There's nobody there to use a GPS receiver there. But so the back lobes of radio energy don't go out into space. They're only pointing down towards the Earth. But it turns out that when GPS satellites come around the corner, when they're coming around the Earth, there's enough signal that is going in the direction sort of that the satellite is going, that as you see them come around the limb of the Earth, around the edges of the Earth, you can pick up that data from the moon and probably use that to successfully navigate on the moon. Of course, it doesn't work if you're on the far side of the moon where you don't get to see the Earth on the far side of the moon, but that's a different story. I think the thing that I was talking to somebody who's got a project to build a radio telescope on the far side of the moon. That's a pretty interesting thing to do because on the Earth, there's just an awful lot of radio noise going on that makes it harder and harder to make a good radio telescope on the Earth. There's a place, I've never been there, but in Green Bank, West Virginia, is a cell phone-less city, town, because it's near a radio telescope, and there's kind of an effort to keep the things radio quiet in that area. So people who are sensitive to electromagnetic radiation, it's a good place to be because there isn't the usual stuff that exists in most places doesn't exist there. But mostly on Earth, there's quite a lot of radio noise now, and but the far side of the moon, there really isn't any yet. I mean, if somebody tried to put up a constellation of satellites around the moon, it might be a different story. But mostly that hasn't happened, and so you can imagine a big radio telescope pointing out into the cosmos, so to speak, and not receiving radio signals from human activities, so to speak. So, this whole question about what's space to be used for is an interesting one. I mean, there are a few sort of outlandish ideas. So one is to have, in a sense, the cloud be in the cloud. One talks about cloud computing, but one's dealing with centralized servers, and you're sending, all your computation off to some place which is in a data center somewhere. But those data centers are in a definite place. They're in, uh, I don't know, North Carolina, or they're in Texas, or they're in, Washington State or something. But they're there. They're in buildings, often buildings, often in basements, or often buildings without windows, because who needs windows if there's just servers inside? But they're physical places. The cloud is on the ground in a definite place. But one of the outlandish ideas is to say, well, what do you need to run computers? Well, you need power and you need cooling, because computers generate quite a bit of heat. They dissipate a lot of the power that goes into them as heat. So, what better way to have a way to radiate heat than to be in space, where you can just radiate the heat off into space? And what better place to get power than to just have something where you have a big array of solar cells and you're collecting solar power? Why not just run the cloud in the cloud, so to speak? Well, actually, far above the clouds in space. I'm told the latest the claim from somebody who should know, that doesn't quite work yet. That the parameters don't really make sense yet. I mean, there are things that have been done that are important in communications in space, like laser links between satellites. That's an important piece of the story. That if you're trying to, make your phone call or something from here to there, that the actual sort of phone signal is being, you are communicating with one satellite, it's sending a laser signal to another satellite, and that's the one that, and then it will send down a radio signal to Earth, to be the other end of your phone call. But so the cloud in the cloud isn't quite there yet. But so what else? Well, another thing people talk about that at first seems a bit nutty is put heavy industry on the moon. I don't know. I'm certainly the cost of launching things into orbit and then even taking them to the moon, is going to go dramatically down. And even now they're starting to be sort of almost consumerized. Well, certainly for Earth orbit, you can have a little CubeSat that's a definite size, and you put whatever you want in that thing, and somebody will launch it for you for some fairly modest price. I have to say, sometimes the level of sort of amateurishness of CubeSats can be quite high. I know some people who had the misfortune of building a CubeSat, and the thing got launched, it got deployed in space, and they lost it. They couldn't, it was tumbling probably, and its antenna was not pointing towards the Earth, and they just couldn't communicate with it, and it's just out somewhere, probably being detected by, folks like NORAD and so on, who scan space with radar to see what's out there. It's pretty easy to see that there's a metal object in space, because it reflects radio signals in a way that space alone does not. But in any case, so it's become quite consumerized to send a CubeSat into space. I think it will very soon become quite consumerized to send something to the moon, which is kind of interesting. But this question of whether will it get to the point where you can go and start sort of doing manufacturing of things on the moon. Certainly if you don't want to pollute the Earth's atmosphere and you've got sort of messy stuff, you could potentially do it on the moon and send all those pollutants out into space. That's not yet completely convincing to me. The thing that people talk about is, what could you make on the moon? One thing you can make on the moon is rocket fuel, because it's become clear there is water ice on the moon. And water ice contains hydrogen and oxygen. Water is H2O, two hydrogens and oxygen. So if you can crack that water into its hydrogen and its oxygen, then you have rocket fuel. You can take the hydrogen and separately the oxygen, and then the rocket can be burning that and combining the hydrogen with the oxygen, producing water vapor, and producing lots of energy. And that's a propellant for rockets. And so one of the things that's kind of interesting is you can, if you want to kind of provide fuel for rockets in Earth orbit, it is much easier to do that from the moon than from the Earth, because the gravity of the moon is only 1/6 the gravity of the Earth. But it turns out that the strength of a chemical rocket is sort of constant. And if you're launching from the Earth, I forget what the number is, it's like only 2% of the mass of the thing you're launching winds up sort of in space. Most of the mass that you're launching has to be used up in the fuel that you're burning to get you to orbit, for example. Whereas on the moon, it's, I don't know what the numbers are, maybe more like 50%, because of the lower gravity and the fact that you've got a constant amount of force that you can generate with a chemical rocket, that you can get much more of the mass that you start with can wind up actually being in orbit there. That's why, for example, in the Apollo missions, when the LEM, the upper part of the LEM was launched back into lunar orbit, it doesn't have giant fuel tanks. That it can have fairly modest fuel tanks to still be able to make it to lunar orbit. So the idea is, if you've got fuel that's made on the moon, you can deliver it to satellites in orbit around the Earth, and you can do that much more easily than you can getting fuel from the surface of the Earth to those satellites. And for example, it's relevant to have fuel to satellites because that's what you need to get satellites to move to higher orbits, things like this. I mean, in modern times, there are enough satellites in orbit around the Earth that there are collision avoidance maneuvers that have to be done routinely, I think many times a day at this point. Because if you've got two satellites, they're both orbiting the Earth at about 17,000 miles an hour if it's low Earth orbit. And if they're going in opposite directions and they run into each other, that's kind of bad news. And so they have to, it's fairly easy to detect where the other satellite is just with radar, but then you have to sort of evade it, and that takes some fuel. I think also things happen like, for example, if the sun is going to sort of belch out a coronal mass ejection of plasma from the surface of the sun, that happens from time to time. It blows past the Earth. It has a big effect on satellites. It can kind of burn up their electronics. And let's see, why does one have to do this? One has to move satellites from low Earth orbit. Oh, I know why it is. Yeah, it's because when that happens, that causes the upper atmosphere of the Earth, I think the thermosphere part of the atmosphere, to expand, I guess because it's heated by the plasma that's coming by. As that expands, it causes more gas to exist at the altitude that the satellites are orbiting, which causes them to have more drag, which causes them to be sort of pulled down and burn up in the Earth's atmosphere. So to avoid that, you have to raise the satellites up. And I guess there's a big effort to give people more warning. It's like, to get it down, to get it up to, maybe a couple of hours of warning of, oh, there's a coronal mass ejection coming this way, move the satellites up to avoid them getting pulled into getting their orbits decayed. And I guess the good news is that you see the coronal mass ejection happening. There's a spacecraft that's close to the sun that sees that, and it takes light 8 minutes to get from the sun to the Earth, but it takes the coronal mass ejection, I think, a couple of days to get from the sun to the Earth. So you have time to do things. So let's see. I mean, in terms of other applications of space, there's people talk about mining things on the moon. They talk about mining helium-3 on the moon. They talk about mining things from asteroids. They talk about, I don't know, what are some popular things, maybe tantalum, rhenium. I forget what the things that people talk about mining from asteroids. But certainly rare earth metals are a thing that certainly exist in asteroids. And on the Earth, there are deposits of those things. Sometimes there may be deposits in places on the Earth that are in countries that you don't want to do business with, or that are hard to access or whatever. And so I guess it's more convenient to go fetch them from an asteroid in that case, although that's clearly a fair amount of effort. Then, there are all sorts of other applications. For example, another question is when it will make sense to have kind of rocket-based communication from one part of the Earth to another. I mean, back in the Cold War period, sort of everybody talked about ICBMs, intercontinental ballistic missiles, where you launch them from one place on the Earth, and then an hour later, it's kind of attacking some other part of the Earth, and you can get sort of from anywhere to anywhere in like 90 minutes on the surface of the Earth if you are prepared to sort of go up into the place where you will be in orbit and so on, and come back down somewhere else. And so there's a question of when's that useful, and are there applications where you can use that? For example, if you want to if you're very impatient going from from Australia to Europe or something like this, go in a rocket type thing, then you can get there quickly. I have to say that for myself, my sort of go faster type thing in terms of transportation and travel, as there start to exist cell phones and internet connectivity and so on, I'm not sure I mind that much that it's slower to get from here to there than it could in principle be. I mean, I remember one time when that was still a possibility, I took a trip on the Concorde because I was going from London to New York at a time when it was, I had events going on at the two ends, and it was like, okay, I can get from here to there by taking the Concorde because it's much faster than a standard plane. But at least for me, it's sort of a rare use case, and I think in modern times, I would have been like, oh, I'll just arrange things differently and take the slow plane, so to speak. But in any case, for human transportation, it's not clear, to me at least, the value of sort of that fast transportation. Although maybe there are, it might be convenient, it might be nice, I suppose. But I mean, you could say I could be arguing, why take a plane? You could go on a boat. But that's and that maybe is a bit silly to say that. So maybe if there was a hypersonic suborbital way of getting from here to there, then it would be like, that's great. There are other things like, I don't know, medical things where you're sort of well, again, that's a thing that will be solved with different technology probably. If you have some organ to be transplanted, and you really want to get it from here to there before things start to die off. I mean, my guess is that will be solved by better sort of cryonic storage of organs, and that won't again be so critical in terms of timing. And then, of course, there are military applications. If you want to deploy, some fleet of drones or whatever else in a different part of the Earth, then sending them there quickly is something potentially pretty convenient. You're not sending a plane that's going to take 12 hours to get to where you're going. You're sending a rocket that's going to take an hour to get there. One hopes that the world is a simple and peaceful enough place that none of that is necessary. But the reality of human history has been that, unfortunately, one would like to say, oh, the world's getting more peaceful, the rate of wars and so on is going down, but I don't think that's what the data actually shows. And I think it sort of sadly probably comes with our species, so to speak. Let's see. Gosh, lots of questions here. Ollie is commenting, do you think humans could or will evolve to adapt to space travel? Well, I mean, we humans are evolving in strange ways because the way that biology, unless you go in and change genomes, unless you go in and edit our genomes, which is becoming more possible now, what will happen over the course of generations is just natural selection. That is, whoever survives and produces lots of kids is the thing that wins. Now, the fact is, from a physiological and biological point of view, that kind of sort of natural selection is definitely on the way out in terms of human populations, because the uh, things which would be sort of problems, mutations that cause problems, one can fix those medically often. So, I think it's already the case in some places that, the typical kid who's born who has some weird features will get their genome sequenced, and maybe it's just like, oh, they're missing this enzyme or something. Great, they should take this pill every morning, and admittedly, right now for life, so to speak, to fill in that enzyme that their genome didn't make. But in the past, that that person would have died. Um, but now, medicine has patched that up. And so, that trait could then be passed on to their children, et cetera, et cetera, et cetera. So you don't get the same sort of dynamics of the struggle for life it's a good thing, but that existed in sort of most of the history of biological evolution. I mean, the difference is that nowadays there are all sorts of perverse forms of selection. For example, countries where there are lots of people who are better off, so to speak, tend to have less children. I mean, there are countries like, I don't know, famously South Korea, for example, where the rate of production of children is far less than is necessary to keep the population as it has been. And so, it's a sort of perverse thing. It's kind of the folks who think they have better things to do than have children. I think children are a great investment. I have 4 children myself, so I'm not I'm not I'm contributing to the non-extinction of the species, I hope. The that the kind of, there are places where sort of whatever cultural things there are, or economic things for that matter, there are that lead people to have fewer children. That is the modern form of natural selection. The modern form of natural selection is cultural and economic in a sense, rather than the traditional kind of struggle for life type thing where people didn't make it to childbearing age and things like this. But so what about in space? You know, I have to believe that if there's a Mars colony or something like this, that it, I don't think people are going to, I don't think anybody's going to want to set up the Mars colony. So people who are, not suitable for Martian gravity or something like that just die. That isn't, nobody's going to want that. I mean, in many visions of sort of a Mars colony, it's kind of utopian play. I don't think the utopia includes you leave the people to die if they don't adapt properly to Martian gravity. So, I think the notion that uh, uh, you get kind of adaptation that way is not real. Now, it could also be that the people who choose to go off and hang out in a Mars colony will have some characteristic. I mean, if you choose to be, I don't know, a fighter pilot, I think, you're not, if you're tall and lanky and, have all kinds of issues getting blood to your head, then you don't want to be flying in a plane that, puts you under 5 Gs of gravity and pulls in your blood, in some weird direction. So in a sense, there's an occupational selection process that's operating there, where if you were sending people to the Mars colony, and it turns out, I don't know if it's the case, that if you're I think about it, it's not obvious. If you're sending people to a colony on a planet that has higher gravity than the Earth, then there will be different kinds of things you would want. But lower gravity, I'm not sure what the actual criteria might be, but it could be that there will be sort of selection in, who wants to go to the Mars colony because, gosh, you wouldn't have a good time there. I mean, like for example, if you have, clearly, if you're allergic to some kinds of plants, you're not going to go live in a place on the Earth that has those kinds of plants, or probably you're not going to. And if you have a choice, you're not going to do that. And so there might be some bizarre form of selection of sort of who chooses to go to the Mars colony. But I don't really see a mechanism unless one is going into kind of the rather scarily eugenics type territory of let's edit the kids who are born on Mars type thing. Let's edit their genomes to make them more Mars compatible. That seems like a very difficult ethical issue, because it's like you have a kid, the kid has been made Mars compatible, but then the kid says, I really want to go to Earth. and it's like, sorry, you're out of luck. You know, you'll be crushed if you go to Earth gravity type thing. That doesn't seem like a good, you know, it doesn't seem like an ethically sensible direction. You know, when it comes to sort of if one's thinking about, for example, interstellar missions, there's a lot of physics we don't know about how to make an interstellar mission. But, you know, if you have a spacecraft going to Alpha Centauri or something and taking, you know, I don't know what, thousands of years to get there, well, one choice is you got some humans there. One choice is no humans, just AIs, so to speak. But if you think, well, you got to send humans there, um, then um, you know, I suppose another choice would be if you figure out how to artificially grow a human, so to speak, from DNA, you could just send AIs and DNA, and then it gets to that lovely planet, that great tourist destination around Alpha Centauri or something, and then the AIs say, okay, let's make some humans now. Again, an ethically kind of complicated thing because you're then creating humans who are fated to be near Alpha Centauri. You're kind of setting up, it's kind of an inverse version of, you know, you're sending them off to the sort of distant penal colony type thing. Instead, they have, I mean, I suppose none of us have choice about our birth, so to speak. So I suppose it might be no different. But it's a slightly strange choice to make. Okay, you're going to create these humans who are going to be born on Alpha Centauri, so to speak. But you know, the other possibility is they're humans who are sort of you know have been around on Earth, and then one if cryonics starts working, you freeze them for the 1,000 years they might be in transit, and then they sort of they thaw and they wake up again, and then they're like, okay, now we're you know in Alpha Centauri, etc. I think it'd be, but you know, the other possibility is that you have you know a starship with many generations of humans. I think that is pretty doomed because I just think if you're dealing with 10, 20 generations of humans, where each of those intermediate generations knows only the insides of the starship, I don't think you'll end up with humans with any kind of cultural connection to the humans that you started out with. And you know, they arrive on Alpha Centauri and they're like, what do you mean there's a planet here? We don't want to be on the planet. All we know is the inside of the starship. That's what we're happy with. Or they'll all kind of, from our point of view, looking at it from the outside, sort of go crazy and kill each other, and you won't have any humans left on the starship. I don't think we humans are well adapted. I mean, maybe that's a case. It's a rather grim possibility, but maybe that's a case where there will be natural selection because, in a sense, the humans who are going to make it are the ones who are prepared to hang out for 10 generations in this starship. I mean, it's a very bizarre kind of type of existence because you know, on the Earth, there might be great works, you know, the cathedral, the pyramid, whatever else, that's not going to be finished for several generations, and you are contributing to it at one stage. I mean, I suppose those of us who work on science and so on, we know we're contributing to something which sort of is our generation's contribution, and we're not going to get to the end. There isn't an end to science, so at least we don't have to be, oh gosh, it's so sad. I'm living in this time in history, and if only I lived 500 years in the future, you know, I would see the end of science. That's not a thing because science doesn't have an end like that. That's something we can understand from computational irreducibility and so on. But in any case, so I think it's not. I don't see an immediate sort of adapt the humans to space travel. I think the more likely thing is that people, you know, people on Earth, you know, we wear clothes and things like that. Maybe if you're hanging on some other, you know, somewhere else, you'll wear an exoskeleton, so to speak. Actually, I saw some nice exoskeletons. I didn't have a chance to put one on. I could have done, but I didn't have the time at this event I was just at to put on an exoskeleton and see what it feels like, so to speak. But that's you know that's something it could become the routine thing. Okay, you're hanging out on the moon or something. I'm going to wear an exoskeleton that somehow puts forces on my body that adapt kind of moon life more to what I'm used to as a human who's evolved on the Earth. Let's see. Gosh, so many questions. Tor asks, if you could teleport to the moon or Mars instead of travel by spaceship, would you take that travel option? Kind of depends on how the teleporting works. I mean, if somebody says, hey, let's take some of your DNA and grow a clone of you on, somewhere else, and then, let's say it's been successfully possible to kind of read out all the stuff in my brain. Let's make the clone of me and have it go hang out on Mars or something. That's one thing. I guess that the clone of me doesn't feed back to me the memory when I come back to Earth, so to speak, of what it was like to go hang out on Mars or something. But that's a form of teleporting that I can imagine working. I think the physics of you're here, you're going to go somewhere else, and you are the same you, so to speak, I don't think really works out. In our models of physics, it is in principle possible to go faster than light, but not as a thing like us. By sort of gaming the structure of the underlying structure of space, you can have sort of things where the effect, in some sense, can go faster than light. But the thing that's going faster than light is a thing deeply different and very distinct and very, very incompatible with kind of a minds like ours, so to speak. So I don't think one gets to do that. But in principle, well, it would be fun, I suppose, to be able to have sort of virtual tourist experience on Mars. You're walking around on Earth and you've got your VR headset, and you maybe have some actuators that give you a different sense of gravity and so on. And it's like, hey, I'm hanging out on Mars now. There's a bit of a problem, which is that the light travel time from Mars, it varies with time with orbits and so on, but it's like 20 minutes. So if it's like, I'm going to see what happens if I want my avatar to reach out and grab that rock and take a look at it for me. Well, the problem is it can take, you are sending the signal out that says, hey, move your arm to grab that rock. 20 minutes later, or 40 minutes later even, it's kind of like, okay, you grab that rock, now you can see it. So you have to be there to make that work. To the moon, it's more like a 2-second delay. I don't really know what that would be like to be kind of navigating something or where you're kind of controlling your avatar on the moon, but there's that delay. I mean, I guess the folks who drive rovers and things around on the moon routinely deal with that issue, although most of those rovers at this point have semi-autonomous operation, and they kind of define waypoints, but then the rover itself is driving for a while until it gets to that waypoint because of this issue. I mean, same thing happens on Mars with rovers on Mars. You just can't send them real-time instructions. And so you have to rely on a certain degree of autonomy just because light can't get there, radio signals can't get there fast enough. Let's see. Right. So Rebel is commenting, space is a hazardous place compared to Earth, with things like radioactivity from cosmic rays and the solar wind and so on. Chips in space would need to be very shielded and hence expensive, they say. Yeah, that's true. I mean, usually there are military specification chips or radiation hardened chips that are, when the chips come off a production line, well, some of them have different characteristics. Some of them are just, oh, this one sort of was formed well enough that it can be used in a higher radiation environment. It's that's the kind of thing you often have to do. I mean, the most extreme case in our solar system is Jupiter, because Jupiter has a very intense magnetic field that picks up all these particles, probably mostly from the solar wind, the particles streaming out from the sun. They get picked up by the magnetic field of Jupiter, like on the Earth. The Earth has a magnetic field as well, much less intense than Jupiter, but the Earth's magnetic field picks up particles, mostly protons and electrons from the solar wind, particularly electrons, I guess. And when it picks up those particles, you both get the Van Allen radiation belts around the Earth, but you also get particles spiraling in around the field lines around the north and south poles of the Earth. And that's what gives you the aurora when those high energy electrons interact with typically, I think, oxygen in the upper atmosphere. You're exciting oxygen atoms, and those oxygen atoms that have been kicked by a high energy electron coming from the solar wind, spiraling in on on those magnetic field lines. When that oxygen atom gets kicked, it produces light at a characteristic frequency that can be orange, it can be red or green or whatever else, and that leads to the aurora. Well, on Jupiter, that whole thing is much more intense. And around Jupiter, there's just extremely high radiation. And the spacecraft that have gone to Jupiter have had this little vault, typically, where you keep the sort of the valuable electronics in this vault. And I'm trying to remember what material that vault is made of, because you would think it was made of lead, which is a good insulator of radiation, but I think it is not. I think it's made of something else, and I don't remember exactly why. You would think that you would need something which has high atomic number, large number of protons in the nucleus, but I seem to remember that it actually isn't, perhaps because you get too many secondary electrons and things when, I'm not sure. But in any case, the idea is to have this sort of vault where all the electronics is inside this box, inside the spacecraft, because that's at least all the low voltage electronics, because that can be shielded from radiation. Now, when it comes to sending people, people get exposed to radiation in Earth orbit and certainly in deep space. And what it will be like if one is sending folks out of the sort of the shielding provided by the Earth's magnetosphere, and sending them out for a long time, like on going to Mars. I don't know what the current designs are for this. I mean, there was talk a while ago of sort of storing the water for your spacecraft in kind of the outer coat of the spacecraft and using that as a thing to provide radiation shielding, because you need to store water and you need radiation shielding. That's one possibility. I mean, it will certainly help if you can make rocket fuel on the moon. It will be possible to send much bigger, heavier spacecraft to Mars in that case, which makes it easier to put shielding into them and so on, to prevent the fragile astronauts inside from getting exposed to all that radiation. Let's see. Okay, there's a question here from Double. Why don't we use shielded nuclear waste to heat buildings, like in the basement attached to the HVAC system? That's a funny question. I mean, on spacecraft, there are sort of two ways you can get power to a spacecraft, basically. One is solar panels. That's great if you're fairly near the sun. And one is to use a nuclear source of power. For example, the Europa Clipper spacecraft that launched recently to moon of Jupiter, that has great big solar panels, which are getting power from the sun, even though the sun is just a pinpoint of light by the time you get out to Jupiter. Actually, the Europa Clipper spacecraft, I believe the systems engineering for that was done with our fine technology, no doubt figuring out a bunch of the power budget for that spacecraft and, just how big do those solar panels have to be to supply the power you need to run all the instruments and so on for that mission. But in any case, many missions to outer planets and so on, most of them have used RTGs, radiothermal generators, and those are pieces of plutonium, for example, that gradually decay radioactively, and the radioactive decay doesn't produce any nuclear effect. Instead, it's just nuclei are blowing up, and the things they blow up into are particles that have high energy. As those particles are absorbed, they simply heat up the material. And so you have this kind of source of heat from that. Now, the fact is, people who be building those spacecraft have had a very hard time in recent years because the supply of appropriately enriched, I guess it's both uranium and plutonium, has been quite depleted. So they've had a hard time getting enough to put in their spacecraft. So I don't think it's a consumer type of thing to say heat your house that way with kind of a radiothermal generation, because if you can't get it for that one spacecraft every few years, I don't think you can get it to heat your house. At least not until there's a lot more nuclear reactors in the world that are generating a lot more. Because once you have a nuclear reactor, you can use the neutrons and things from that nuclear reactor to bombard otherwise kind of happy non-radioactive materials and make them radioactive, and get and sort of get your fuel that way. Elsie is asking, what do you see as the short to medium term future for inhabited orbital space stations? And then in the longer term. I don't know what the number is so far. I remember maybe a year ago, there was a day when there were 17 humans in space. There were 17 humans off the planet, and that was a record up to that time. I don't know how the number of humans off the planet is going to ramp up over the course of time. But there's a question of who wants to hang out in orbit and why. And I don't know what, there's space tourism, but there's also, is there more to do in orbit? And that depends on, well, what is there to do in orbit? You can be repairing satellites, maybe, if that's not done by robotically. You can be, doing experiments, but I don't know how many experiments there are in the end that, there's always more science to do. But I'm not sure, quite how that scales. If you had 1,000 people on space stations in orbit doing experiments, would that be useful? Would there be another level? I mean, what often happens with technology is there's a thing where, well, with a big stretch, you can get to that point and it gets done once or twice. And you can learn a certain amount from that. Then there's it becomes routine to do this. And then there are very different things one can learn. I mean, I know for myself, I've been building the stack of technology for a long time to automate lots of things. And, that's what our Wolfram Language technology stack does, is to automate a lot of what one wants to do computationally. And I've seen over the course of years, gradually things sort of get over the horizon. They're things that become so easy to do that you can just do them on a whim. And so if it became so easy to do an experiment in microgravity in Earth orbit, for example, that you could sort of routinely do those things without having to think very hard about what you would want to do, maybe that will introduce a whole nother level of sort of scientific and technical advances. I don't know. But from what I know right now, it doesn't seem like there's a huge queue of, if only we can do, 5 times more experiments. Maybe that's wrong, but that's at least my impression from a distance. So, that leaves things like space tourism. And I think space tourism will surely be a thing. I don't know, there's tourism in the oceans, there's tourism in Antarctica or in the Arctic. The number of people who are that excited about doing that is somewhat limited. But that's, in a sense, easier to do than to go to the moon. At least it has been easier to do than to go to the moon. Maybe spaceflight will become so routine that it's easier to go to the moon than it is to go in a submersible deep in the ocean. I can't imagine it will be easier to go to the moon than to go to Antarctica. So the fact that there isn't a huge demand for Antarctic tourism, for example, even though I'm told now many people have gone there and even spent a bunch of time there, I'm told it's really sort of visually very stunning. And, it's fun to see the penguins type thing and all that. Let's see. Let's see. Well, from genetic issues to space travel damage, do you think main advances will come from preventing or repairing that genetic damage, or both? We all accumulate genetic damage as we go through life. So if we can repair genetic damage, that's a pretty cool thing to be able to do, just to sort of reverse aging and so on, because a lot of aging is a consequence of genetic damage to the DNA in our cells, to our mitochondria and their genetic sequences and so on. So if we can find something that fixes that, that's something that is a pretty cool thing for us here on Earth. I mean, it's a routine thing. If you have some population and you're trying to kind of shake it up and get more genetic variation, you're getting more mutations, it's an absolutely routine thing to do, to expose whatever you have, your yeast cells or whatever, or to radiation. And that's a way to kind of cause there to be more mutations. So, absolutely, radiation causes more mutations. Can you fix the mutations? well, you kind of have to know what you're fixing them back to. But yeah, that's a thing that will be useful. If one can do that, it'll be useful for more than just space travel. Okay, I think I have to go back to my day job here. All right, maybe one more question, if I can see something quick here. Gosh, you guys are asking all kinds of interesting questions. Can't wait to try and address some of these. Um, uh, yeah, this one is going to get us too far afield, but there's a question here from Sushi. How would you think about AI-controlled humans if bionic brains become mainstream? That's a very philosophically challenging question because it's like, uh, you know, what do you mean it's a human? If, let's say you've got this sort of brain stimulator that is AI based and it's kind of making you do this and that. It's like, um, this is going down a path where you don't really have a human anymore, and where you just have sort of, there's meat packed around an AI core. It's a very strange thing. I was just seeing this there's a company that has been growing kind of, they were growing organoids, sort of collections of nerve cells. Now they're growing, I think, just layers of nerve cells on semiconductors and using that as a way to do kind of true neural computing, not with artificial electronic simulations of things a bit like nerve cells, but actual nerve cells connected to electronics. And that's kind of the other way around, rather than taking a human and kind of hollowing out, starting to attach things in the brain to get the brain to do particular things, a very ethically challenging issue. That's to me, a very ethically challenging issue. Sort of the other way around is it's kind of electronics in control, and you're putting a layer of neurons on top of that. And then again, complicated ethics at some point. I mean, I don't think it's very complicated ethics when you're dealing with a small number of nerve cells, but by the time you have a large number of nerve cells, it's complicated to know what that means. I mean, in the case of when it comes to humans and kind of sort of putting more structure into the humans, I saw actually at this event I was just at, people who are interested in putting little tiny sort of drilling through the skull and sort of putting little actuators, electromagnetic actuators on the surface of the brain outside the meninges that surround the brain, the dura. Yeah, I guess that's the generic name for that kind of skin around the brain. And sort of sending electrical signals in that way, maybe to treat depression or something like this. But you can imagine a more extreme version of that is you're sort of just telling the brain what to do. And certainly one can do sort of the demo of you can at least get fingers wiggled by exciting the motor strip in the brain, and to get to sort of to puppet the human into doing certain kinds of things. I think what does it look like then? What is it like? I mean, by the time there's an AI sort of telling the brain what to do, it's kind of like you've got an exoskeleton that's moving your arm, except it's more upstream and it's moving what you think. It's, if you talk about sort of mind control, so to speak, that's the ultimate version of it, is you're just sending electrical signals that are coming not from your internal brain electrical signals, but instead from something that's actuating the electrical signals in your brain. How should you think about that? I mean, people might say, hey, I want to treat this or that psychiatric condition that way, and I want to make this person able to be more functional in the world and more normal as the rest of the world thinks of it. And maybe that's an obvious, in many cases, that's an obvious win. But by the time you're like, well, I want to make myself be more motivated to, I don't know, it gets very complicated. I mean, it's like, okay, I want to make myself be less hungry. Okay, we can do that with certain kinds of drugs, but let's say we could do that by brain stimulation. Or I want to make myself like the color purple more than the color green. Maybe I have a reason to want that. But it goes down a pretty slippery slope of saying, what is it that is our kind of free will versus of things happening internally in our brains, and what is it that is merely the puppeteer AI that's sort of telling us what to think? Obviously, there's a certain amount of sort of telling us what to think from the way that the external information coming from the outside world, but by the time it's internal, built right into your brain, you can't like look away and not read that or not see that. It's right there in your brain, and I think it's a pretty complicated thing to think through what you do, because for example, you might say, well, in the morning I want to decide what kind of a person I should be today. And then you say, well, I'm going to set my brain up to make me really enthusiastic about doing this or that kind of project. And in the course of the day, I will be really enthusiastic about doing this kind of project. I'll really feel enthusiastic about it. If I really think about it, I know, well, I just set that this morning. Does that affect how I think about it? Can you break out of sort of that, the bionic thinking, so to speak? It's an interesting question, whether you get to the point where I can't help myself but to do this, but I know that I set myself up for this. Can I press the kill switch, so to speak, to stop myself doing it? Or am I so sort of burnt into doing it by the fact that my brain is being actuated to do it that I just can't even get to that? And then how does one feel about, it sort of gets a lot into kind of the personal identity that one has and so on. It's that's it's really shines a bright light on the questions of what is it to be human, so to speak, and what do we imagine? Right now we have sort of a pretty simple workflow in some sense, purely biological. Humans, we exist, we live, we have a certain lifespan, and so on. Many of us have children, the children go on for another generation. There's not a lot of, we might have cultural things that we affect, but we don't, there's no kind of, we just live out our lives and do what we do. And it's not something where there is a sort of direct constraint from the outside about how we think about things. It becomes much less clear, when you say, it would be nice if everybody lived a fulfilled life. What does that mean in the case of, in the case of where you are sort of being puppeted, life, liberty, and the pursuit of happiness, so to speak? What does that mean in the case where there's an external AI that is kind of determining what, the liberty isn't quite the same thing when there's sort of an external AI that's making you think you're doing exactly what you want. But, you are thinking that you're doing exactly what you want, but the origin of that thinking is from the outside. Now, at some level, that's no different than sort of cultural effects. It's no different from the fact that we're all, have a certain imposition of culture on us that makes us think these things are worth doing, those are not, these are good, these are bad, and so on. So at some level, maybe it's just a more intense version of that, but it feels a bit different. And it feels like the sort of, you can't escape from this, it's actually burnt into the operation of your brain, makes it a bit more difficult. Well, with that, I think it's time for me to go back to my day job. But thank you for a lot of very interesting questions, and I look forward to continuing another time and having a chance to address more of these questions. So thanks very much, and bye for now.